Hello and welcome to my water lab presentation. We will be determining the composition and concentration of ions present in unknown A. Also, Simon said I will mark generously, so I hope that's true. To analyse our water sample, we'll be using three main techniques. So the first one is qualitative analysis, and this is simply seeing a precipitate or a specific colour in a flame test. The second one is using spectroscopic analysis to determine the concentration of ions, and the third one also determines ion concentrations, however in a much different way, and this technique is called inductively coupled plasma. So what is qualitative analysis? So water samples will contain a variety of different ions and chemical species, and these can be identified in a number of ways, but the easiest way to check to see if an ion is present in the solution is using their insoluble precipitates. The only problem with this is you won't be able to get any information about the concentration of an ion or anything like that. You'll just know that the ion is present. For example, a simple test for silver ions is to form silver chloride, which is insoluble in water. So you have silver ions, you add something like sodium chloride, and it will form silver chloride, and you'll be able to tell if you have silver ions in your solution. So there are 5 groups that can be identified using these techniques, and 4 of them use the precipitate technique. So the first group form insoluble chlorides. So we've got silver, mercury, and lead, and the colours, they're all white solutions, so the colours will be the colour of the actual ion there. So group 2 is in acid, but it's the insoluble sulfides, so we've got bismuth, copper, cadmium, antimony. And group 3 is sulfides again, but in base this time, so chromium, aluminum, iron 2+, iron 3+, nickel, cobalt, zinc, and manganese, which are quite nice and pink. And we've got group 4, which is insoluble carbonates, so magnesium, calcium, barium. And the final group, the ones that aren't identified using the precipitates, we've got sodium, potassium, and ammonium ions. So ammonium ions will turn litmus paper blue if they're present, and sodium and potassium you use flame tests for. So you've got a nice yellow and a nice lilac colour. Once you know what ions are present in your solution, you can use other techniques to figure out their concentration. For example, inductively coupled plasma, or ICP for short. So ICP works by sending argon gas into the machine, where a Tesla coil ignites the argon gas into an electron and a positively charged argon ion. And the resistance of this electron within the magnetic field in here will produce a lot of heat, and this is where our plasma generation occurs. So a plasma is just an ionized gas, so in this case we've got a positively charged argon ion and an electron. And this can reach a temperature of 7 to 10,000 Kelvin. So the next step is to run our sample through this plasma flame, and the ions in the sample will enter their excited state. So this is much better than a normal flame test, as it's much hotter, so almost all, if not all of our sample will enter their excited state. So once they're in the excited state, they return back to their ground state and will emit a photon at a specific wavelength of light. So each different metal has a different wavelength, so that's how we can determine this. So the final bit is for the lenses and or mirrors to amplify the signal, and that's how it gets to the detector. But another good thing about this method is not only can we identify ions, we can also determine their concentration, which is the whole point. So a larger presence of a specific ion will lead to a more intense signal, and from this we can figure out calibration curves and the like. So for example, here's a calibration curve for arsenic concentrations in blood. So say these samples are all the same size, but this one is going to have a much bigger arsenic concentration. So we will have a much more intense signal compared to the ones further down. So if we have an unknown sample, we can look at our intensity of the signal and then figure out the concentration from there. So that's one way of determining the concentration of the ions you know you have. Another way to determine the concentration of ions in our solution is to use a technique called UV-Vis spectrometry. So this is based on the idea that a concentration is directly related to its light transmission, and this is demonstrated in the Beer-Lambert law. So the Beer-Lambert law states that the absorbance is equal to the path length times the concentration times the molar extinction coefficient. And this works in a similar way to the ICP technique, where you can use different known concentrations to form a calibration curve, which you can then use to find out the concentration of your unknown solution. And here's a picture of a UV-Vis spectrometer that is similar to the ones that we use in the laboratory. There is also a third way to analyze the contents and concentrations of your solution, and that is by using ion selective electrodes. So these electrodes are used to determine the activity of a specific ion, and they generate potentials in the presence of specific ions. So they can do this because they have membranes that only allow a specific ion through to the electrode. So there are different types of membranes, for example, glass, crystalline, exchange resin membranes, or even enzyme electrodes. And these are extremely useful, especially when there's multiple ions present in your sample. And the maths behind this is described by the Nernst equation. So the Nernst equation is there on the screen. So the laser pointer on it. So E0 is a constant value specific to each membrane. And then there's a bunch of constants, and N is the charge of the ion. So the only problem with these is they don't always work perfectly. So for example, a silver chloride ion selective electrode will have no interference on like fluoride, sulfate, or hydroxyl ions, but ions such as sulfide and bromide can interfere quite considerably. And here's a little picture, a little example. So here's our solution with lithium ions, and then the electrode, and this membrane here only allows lithium ions through to the electrode. So the first step to take when analyzing a water sample is figuring out what ions are actually present. So to do this, we'll use qualitative analysis techniques as previously discussed. And yep, I am going to use the flowchart from the summer assignment because it is quite nice and very easy to follow. I won't do this for the other groups because you get the point, but it's quite nice to go through at least one. So to identify the group 1 cations, we'll add some acid to our water sample and centrifuge it. And we can add some more acid after this to make sure we've got all the precipitate. And all of the centrifugate will be kept for further testing. And the precipitate, the solid, we can wash it and add some more acid to it and centrifuge and repeat the process and so forth. So once we've got our centrifugate, we're going to do a test for lead ions. So the test for lead ions involves ethanoic acid and potassium dichromate. So once you've added these, if we see a yellow precipitate, that means we've got lead chromate and our solution is lead ions, but it doesn't, so we'll carry on. So we take our precipitate down here and add some ammonia, and then we'll stir it and centrifuge it, and if we see a grey precipitate, we'll see mercury ions, which again we don't have. They sound quite dangerous in water, but we carry on. So we've got two things we can do with the centrifugate now. So we can either add a potassium iodide crystal, and we will see a white precipitate, and that indicates we have silver ions in solution. Or another way to identify silver ions in solution is to add some nitric acid, and this will instead create a creamy yellow precipitate of silver ions. And here's the two pictures. So those are the pictures from the PDF slideshow thing. So now we'll move on to the group 2 cations. So now we know our solution contains silver ions, we can carry on to identify even more ions. So we don't have any group 2 cations, and as I said, we're not going to go through the big flowchart again because once is enough. So one of the first solutions is this one, and this is a zinc solution. So the results we're using states that this should be a red solution, and you can clearly see it's not, but this isn't a problem, it just means we have a different zinc precipitate or different zinc compound instead. And this is zinc hydroxide. This is where the zinc ions react with water and ammonia, get some zinc hydroxide and some ammonium gas. So the other ion present is identified by these red test tubes. So this is a red solution of iron thiocyanide. So there are no precipitate in here, this is just this aqueous compound in solution. And then over here we've got our iron hydroxide precipitate at the bottom in a red solution. So some chemical equations for these, iron 3 plus some hydroxide, get this, and then the same for the iron thiocyanide. So from this we know that our sample has both zinc and iron 3 cations, and we also have some group 4 cations present. So the only test tube we have for this is this one. So this is a white precipitate, and this is manganese carbonate. So that means after all of these qualitative tests, we can determine that our water sample contains silver, iron 3+, zinc 2+, and Mg2+ ions. So now we're at the stage where we know what ions we have in solution, and we can start to determine their concentrations. So we can use spectroscopic analysis to determine the concentration of the iron 3+ cation. So you were supplied with an initial stock solution of iron 3+, and this had a concentration of 5 times 10 to the minus 3 moles per litre. And a new solution was made, and this solution was 500 millilitres, and this was 25 mils of the stock solution made up to the 500 mils with water. And the new concentration of the iron 3+ was 2.5 times 10 to the minus 4 moles per litre. So different volumes of this solution were diluted up to 50 milliliters and used to create a calibration curve. So here are all the concentrations of our new solutions, and at the bottom is the determined concentration of the unknown. So all of these had 3 different absorbances, and the average adsorbance was taken. And this relates back to a few slides ago where we talked about the Beer-Lambert law. So this absorbance here is related to the molar extinction coefficient, the path length, and the concentration. So from this data, we can construct the calibration curve, and it's as simple as substituting in our absorbance for the unknown, 0.817, into this equation up here on the graph. So y equals 0.817, and we can solve this algebraically to find our concentration of the unknown, which is 6.52 times 10 to the minus 5 moles per litre. The next part of the analysis is using the inductively coupled plasma. So here are our 4 calibration curves for the ions we know that are present in our solution. So silver, zinc, iron, and magnesium. However, only 2 of these are assumed to have a concentration after being run through the machine. So we need to convert these to molarities. Obviously these are in parts per million or milligrams per litre. So first of all, you can convert into grams per litre, and it's just as simple as finding the molecular mass, and you can divide the concentration by the molecular mass, and you'll get moles per litre. And this will give us a concentration of 1.63 times 10 to the minus 3 moles per litre for the iron 3+. And following the same for the zinc, we'll get a concentration of 7.345 times 10 to the minus 2 moles per litre. When it comes to discussing this experiment, we can disregard the qualitative analysis. This is because the experiments are extremely simple, and as simple as you see a colour, you know your ion is present. Nothing more. However, when we turn our attention to the iron 3+ concentrations, we can see that the values calculated by both the Uv-Vis and the ICP are extremely different. So we must know that one of these is wrong. And we know that it's going to be the ICP technique because we've identified 4 cations in our solution. However, the ICP only returned data for the zinc and iron cations. So there are 2 potential reasons for this. The first reason being that the sample was not introduced into the machine properly. I'd also like to add it's really hard to determine what these anomalies are because we were not the ones performing the experiment. However, it is safe to say that it was either the samples not put into the machine properly or the calibration curve was messed up or constructed in a bad way. So when we put a sample into an ICP machine, it nebulizes it and then pushes it through the plasma. So if all our sample isn't nebulized, there's a potential possibility of all our ions not getting detected. So we could use ultrasound vaporization, electrothermal vaporization, or a temperature-controlled spray chamber instead as a different method, and hopefully these would make sure all our sample made it into the ICP machine. The one difficulty with this is we know that if all of the sample entered the machine we would almost definitely see a signal for all 4 of the cations. This is because the ICP can measure concentrations all the way down to 1 to 5 micrograms per liter, which is an extremely small concentration. If you've made it this far in the presentation, thank you for watching. And I suppose you need to stay safe, wash your hands, and subscribe, click the bell notification. And if you're bored in self-isolation, go watch the Klein Bottle Man on YouTube. He's quite happy. He's got a lot of Klein bottles. He will keep you entertained. Also, have a nice day inside doing things, and don't get too sad, Simon. You've always got Mitchell's video to watch. Mitchell's videos are always quite entertaining. Yeah, so go and do some chemistry. Go and have a break. Go and watch the latest Avengers movie on your sofa. Up to you, but have a good one.